How is water held? Well, water is held under tension in the soil. And I think one of the best ways to think about soil water in the way that it's held is to think about the soil as being similar to a sponge. Okay? If you have a sponge and you take it and set it in a bowl of water, how much of the pore space on that sponge is going to be filled up? All of it, right? It's going to become saturated. Now, there are going to be different other states of energy that sponge can be at that will correspond to things in the soil. If we lift that sponge out, what's going to happen? We lift the sponge out of the water. What's going to happen? Some water is going to drain, right? And that's going to be the water that's not held against the forces of gravity. That's called the gravitational water. That's water that just moves through the soil. After we get a big rainfall and the soil fills up, it drains for a couple days, and we arrive at a point called the field capacity. And it's at that point that the crop can now begin taking water. The crop is not interested in water in the saturated condition. It's interested in water once that soil has arrived at field capacity, because now we've got some pore spaces filled with air, and the crop can get on its way. How's that water held in a sponge or in the soil? There are capillary forces that hold that water in between particles. That is, if we looked at the water molecule, it has a tendency to grip onto other surfaces. And when there are little small spaces in the soil, a bunch of water molecules are going to all join together and just hang on in there. And that's the water that we're going to be pumping out later for crop use. Here we go. The sponge or soil, either way you want to look at it. You got saturation, you lift it up out of there, or you have a soil after a rainfall for a couple days. Water drains out, it moves from saturation to field capacity. And you'll note at field capacity that there's still an awful lot of pores that are filled up with water. Okay? Plant roots come in there, water's going to be pumped out, and eventually we're going to arrive at a point known as the wilting point. The wilting point is where the crop can no longer obtain any water from the soil. It does not have the energy to exert to suck that water out. Let's back up a minute. How does a plant take water from the soil anyway? Why do we have water going through the plant? Right, not exactly. There you go. Pulls it up. It's a simple force. You got a leaf sitting out here with the sun beating on it. How many of you have ever been out in the sun? I'm trying to find things that almost everybody's participated in. Been outside? How many of you have ever been overheated to some extent and you undergo some vapor loss? Well, it's the same thing that happens to the plant. The plant's sitting out there in the sun. It's got stomates where you have pores, and for a plant it's transpiration, for you it's perspiration. But basically the sun pulls this water out, and in the case of the plant, this water gets sucked out of the leaf. There's a tension applied. It pulls up, gets water out of the stem, ultimately goes down to the root and pulls water out of the soil. So it's just like taking a big suction device and pulling that water up through the plant, and that's what makes it come out of the soil into the plant roots. At a certain point, the plant cannot tug water away from those soil particles, and that's called the wilting point. What happens to the plant at that particular point in time? It wilts. Here again is our literalist, our interpretive guy down here. He picks up on the adjectives and turns them into a thing of beauty. Thank you so much, sir. Glad you're here with us today. This point is amazingly high in terms of the amount of suction that's exerted right there. The amount of suction that happens at the wilting point is about 225 pounds per square inch. And believe me, if that was exerted on the side of your head, and you may have felt like this some mornings, but if that kind of suction was exerted on you, you'd be in bad trouble. So a tremendous amount of suction coming away from the plant. And getting back to our sponge analogy, you take a sponge, you let it drain, and then you squeeze it. The water you squeeze it, it's a very emotional moment. The water that you'd squeeze out would be similar to the water that was used between field capacity and the wilting point. Okay? Is there water still left in the soil at that point? Sure. If you took that soil and sampled it and dried it in an oven, the weight would be less. So there's still water, but the plants can't get it anymore. Here are some different points looking at a soil, the solids, and the amount of water or air, its saturation. Most soils are about half pore space. About half solids, about half pores, 50-50. When it's saturated, it's all full of water. As we come down towards field capacity, about half of that pore space is air and half is water. And we get down to the wilting point or wilting coefficient, it's a lot more air. And then finally the hygroscopic point, which is just air dried, you lose even a little bit more water. Finally, if you took that thing in an oven and dried it down, you'd have all just solid and air for the most part. So those are the different points we talk about. The available water, let's see if we get, oh, something happened to that side, that's all right. Probably been sabotaged here. No, we. Tell you what, let's just go ahead. We'll probably have a potential for greater problems if we look at that. Let me talk a little bit about texture and water supply. We talked about this transpiration rate. If we look at the available moisture, field capacity all the way in the lower left axis and permanent wilting point on the right. If we're looking now at the amount of actual evapotranspiration that occurs over the potential, meaning it's a real hot day out there, you got a wet sand right at the field capacity, what kind of rate are we going to pump water from? We're going to pump water very rapidly for a very short period of time, and as we move on towards the permanent wilting point, the amount of water that we can pump becomes less and less. In a clayey soil, we're going to get a more continuous supply that moves along more slowly. So we can dry a sand out in a hurry. In a clay, it's going to take a little longer. How do you think water would move through a sand or clay as those particular things began to dry out? It's going to move very slowly but continuously from a clay. In fact, in some of our soils in Illinois, we can get motion upward from the water table during times of drought. Very slowly, as the plant shuts down at night, water begins to move up to satisfy that demand, moving into drier soil. Water movement is simply from wet areas to dry areas. That's the way it occurs. How do we determine these points? You might be able to determine the field capacity of a soil on your own, but the permanent wilting point, we simply put these on a ceramic plate and put them in a pressure cooker, and we put 225 pounds per square inch of pressure on them, and we measure the water content that's left. And what we really have then is the difference between field capacity and wilting point is the amount of available water. We measure those 2 points, the amount of available water is what we get in between. How does water move into these particular soils? Well, if we pile up water over a sandy soil, as you might imagine, the water is going to move quicker and it's going to move deeper. It's going to tend to move down in a very straight band. The movement of water into soil under pressure when it's saturated looks for the biggest openings. If it's not saturated and it's just moist, the water tends to wick out. And if we look over here at the clay loam on the right, the movement is slower but much more expansive. That is, the water tends to wick out and move under suction or tension rather than under a positive pressure. Why do we care about soil water? We are trying to meet the demand, whether it be corn, soybeans, or any other crop. During the reproductive stage of that crop growth is the time when we're going to need more water than what the rainfall typically can supply. Those of you that involved in growing corn, of course, you know that regardless of what else happens, if you get a major rainfall right at the time when the silks and tassels are emerging and that grain's first growing, that's when you're going to want the rain. That's when it's going to do you the most good. That's the time of water need. That's when most of our yield is made in any of our grain crops. And our soil water storage is going to chip in during that time, typically to help us cover that area. I think some of the slides that we missed up there would show you different textures moving from sand up to clay loam. And if you draw a line with the wilting point and field capacity and look at the difference between those two, you can determine the amount of available water that's in there. Which textures hold the most water, most available water? Silt loam. And what the deal is with a clay may hold more water at field capacity, slightly more water, but it gives up less water at that 15 bars or 225 pounds that we talked about, the wilting point. So actually the silt loam is about the optimum texture for holding available water. A sand, what do we have problems with? Field capacity, we don't have a whole lot of water, and we don't have much less when it gets to permanent wilting point. The total available water holding capacity is low. 5 foot of soil, nice silt loam in Illinois, how much water does it hold? When I'm talking now about available water for the crop. 12, 13 inches in many cases, okay? So for each foot of soil, you've got 2, maybe slightly more inches of water held against the flow of gravity that crop can exploit. What does that mean in terms of evaporative demand and meeting that? Well, in some of our very hottest days with a full canopy of corn, we might extract about 3/10 to 4/10 of an inch of water per day. That's the amount of evaporative demand. So just like balancing a checkbook, you get 3 to 4/10 demand, you're going to pull that much out of the soil. So how long, if you're using 4/10 a day, an inch of water is going to last you 2.5 days. Using 1/3 of an inch, an inch is going to last 3 days, and so on. So you can get through some periods of a little bit limited water supply with our soil water storage. What we'll do here is get into one of the final 2 sections, talk a little bit about soil conservation and tillage. And for some of the group, most of the cerebral group that has been interested in these high scientific principles in the first half, I want to just let you know that for the rest of you folks that are here, we've got a few more pictures in this particular part of the presentation. What we're going to talk about are different erosion processes, and again, this would probably best be suited to, is that gunshot or bubble gum? Okay. What this would best be suited for, of course, if we could go out and travel together across the desert or the windswept prairie, but what I'll try to do is to make some different noises or give you some visual ideas of what this stuff looks like, and I think you'll be able to get through your test all right. Talk about different wind erosion processes, water erosion processes, factors that affect erosion. These would be some that we can manage, some that we can't. How to estimate residue, there's been a breakthrough in that area. And how to manage for less erosion. Okay, wind erosion. You got a couple of, or 3 basic modes of wind erosion based on how high the particles bounce. For some of you that are old enough to have had one of the early black and white TVs and get in on some early programming, you remember Sing Along with Mitch. Anybody remember this? I'm just barely old enough to have done that. You remember the little bouncing ball? If you remember old Sing Along with Mitch, you'll be able to remember saltation. Just a little short flight, just kind of bouncing along, saltation, moving along, creeping along. Well, better not say creep because that's another one. Saltation, just bouncing along the soil surface. Suspension, as you might guess, and we go back to our expert down here, what would be the condition of the particles if suspension erosion were to occur? He's fallen asleep on us. Would you consider suspension erosion, what condition would you expect the particles to be in with respect to the surface of the earth? Suspended. Thank you. And of course, the material that's suspended is going to be the lightest material. So suspension erosion pulls this up and away. I know that some of you guys with a little larger stature that don't wear belts anymore, suspender erosion might be something you're thinking about. A lot of wear and tear. Surface creep. Surface creep is just rolling along. Creeping, moving slowly on the surface. Surface creep. Anybody need any further clarification on any of those different wind erosion methods? What are some of the factors that might affect wind erosion? Wind? You laugh, this guy would probably get 100 on the CCA exam. Yeah, particle size. And how about cover? Which do you think would erode more, a bare field or one that was totally covered with residue? All right, so cover, wind speed, this sort of thing. I think we're going to be able to get on that okay. Water erosion. A few more little techniques involved here. You got one more method. And these are roughly in the order that they might occur in terms of severity. Splash erosion. If you were to view splash erosion, what would you be seeing, do you think, out in the field? A splash. Right, and this is simply the rainfall energy, the raindrop coming, hitting the surface of the soil and splashing soil particles. Now, I don't know how many of you have a physics background. I'm going to try to see if I can get this point across. If we have a sloping soil and it's wet, and the splash that occurs is going to dislodge some soil particles, and this is sloping soil, remember, what is the net movement of the soil going to be? Even if you don't know the physics of this problem, I want you to think about something. How many eroded piles of sediment have you ever seen at the top of a hill? Okay? The splash comes, the material goes up in the air and goes out to the side, and as it goes uphill, it lands a shorter distance than it does if it goes downhill. So now we get a lot of raindrops on a hillside. Splash erosion is going to dislodge particles and slowly move them downhill. Now, this is kind of a thing where a video with drum rolls and lightning and thunder would be better, but you're going to have to just listen to me instead here. Sheet erosion happens after splash erosion dislodges particles, and we begin to get movement of water across the surface of that soil. And the sheet, in this case, what would be the shape of the water flow? A large sheet of water moving, scouring particles, a very thin amount of particles, off the hillside and transporting them down slope. Okay, then we have a rill developing. And a rill is simply a small channel. These can be corrected by tillage. That's the main way that you would identify a rill, as opposed to a gully. Gully is a deep ditch. It can swallow up a tractor. You can't cross it. Kind of thing I showed you before. Doesn't have to be, quite that dramatic. So we get splash erosion, then sheet, then rilling, then finally gullies. Okay, and those are the different types of water erosion that can occur. Now, our erosion rate is going to be determined by many factors out there. Okay? And the best way to remember these factors, we can do it a couple ways. One is to just intuitively think about each one of these factors and how they might affect water movement and erodibility of soil. Or secondly, remember the little phrase Rickle skip. If you go down here, RKLSCP, Rickle skip, and you can apply a formula known as the universal soil loss equation. It's undergone some modification by SCS. I don't know exactly where that's at right now, but the universal soil loss equation gives us an idea on what are the factors that affect soil erosion as influenced by water. Number one, rainfall factors. The harder it rains, the more often it rains, the greater chance you got for erosion. And what you could do is you'd have a bunch of numbers you could multiply together here to estimate the annual soil loss in tons per acre. K is the soil erodibility, the natural factor associated with the type of soil. What are some of the soil properties that might affect erodibility? Texture. The more silt the soil has, probably the greater erodibility it's going to have, because the silt particles can be picked up and swept away quite easily. L and S are slope factors, length and the actual slope. If you have a long continuous slope, you have a chance for water to build up, and the energy of that water flow is going to cause more erosion than would a shorter slope. And obviously, the steeper it is, the greater chance we have for erosion. C are cropping practices, and these are going to include the type of rotation that you're in. The more often you include a pasture or forages or more complete cover on the soil surface, the less your chances for erosion are going to be. And finally, P for practices. These would be terraces, things like this, different practices that can be added in. What the practices do in this case oftentimes is shorten the slope length. So you get the water traveling for a short distance and it's stopped, and it's allowed to soak in. The whole erosion game, how do we prevent erosion or reduce it? We try to get the water to go in the soil where it hits. That's every practice that you look at, that's really what we're talking about in the end. Soil erosion rate. Now here's a very innovative method that's used, and the math has already been worked out on this so that you can do the calculation on your own on the CCA exam. The line transect method, Sounds kind of high-tech, doesn't it? Well, it's a rope with knots in it. And you go out and estimate the amount of residue by casting this rope across the field and going back and counting the number of intersections that are made with residue, knots and residue. The only thing you need to know on this is that the residue needs to be larger than 1/8 of an inch, and you just count the number of knot intersections. If there are 100 knots in a rope and 47 of them intersect a piece of residue larger than 1/8 inch, what percent residue cover do you have? 47. Got some new math coming in here. No. Oh, it doesn't matter how long the rope is. 100 knots. You can make the rope 2 miles long, whatever. Just what it is the statistical chance of a knot intersecting residue is how many out of 100. So 100 knots, 47 intersections, 47% residue. Okay? That's the deal. How do we control erosion? Well, simply, it's infiltration management. You want the water to go in the soil where it hits. That's the biggest thing. And secondly, to control slope length. What do we do to get greater infiltration in the soil? We manage residue. We manage tillage, and we manage structure. You want an open soil. You want a soil that's got pores where water can go in. And you want a soil that's going to slow down the sideways or downslope movement of water. Allow this water a chance to go in and find the different pore spaces. If the water all goes right into the soil, we have very little or no erosion. If it slides across, we're going to have erosion. Okay? Very simple. Slope length, what you're doing there is breaking the energy, the mass of water coming down. You're stopping it, allowing it to infiltrate. And this is done with terraces or contouring. So any other method that you think of and are asked on the exam, how does this influence erosion? How do we control erosion? Think about what it's doing to water infiltration. More residue. What's that going to do to infiltration? Increase it, right? Because it's going to slow the water down and it's going to protect the structure on the surface. Water's going to soak in. Okay? How about mold board and 5 diskings? What's that going to do? Make a big mess, right? You're going to have lowered infiltration rates. Soil's going to puddle up and you're going to get erosion. So any of your practices, think about what they do to the soil surface and infiltration, and you'll know how they affect erosion. Here's just an old archival photo, as we say, of Soil Conservation Services, the good old days when folks wore hats to work and we had black and white film. And he's in there looking at a gully that's formed. Erosion continues on, and we need to know how to try to keep it slowed down in many of our agricultural areas. I'm going to go ahead and move into the final hurrah here with tillage, and bring it on in for a landing here, maybe a couple minutes early. This is a fairly fun-packed section, though. There's quite a bit of stuff in here. When we look at tillage, I think on your exam, what you're going to need to know, type of things that deal with how tillage interacts with erosion, how it interacts with residue, and perhaps a little bit about how it interacts with crop production. I think, as I've taught this kind of stuff before, and there is some interaction between the different sections in terms of crop production and soil and water management, where you're going to get some different stuff in different parts. I know there's quite a bit of no-till talk in the crop production area, and probably Emerson will talk a little bit about it tomorrow as well. How does tillage affect structure and compaction? The soil organisms. What are symptoms of compaction, and how can we alleviate compaction? These are all really tied into this one big area of tillage. Tillage and crop systems. What does tillage do? Why do we till? Why don't we till? What does it affect out there? Tillage may extend our rooting depth, and I'm going to show you some specific examples from other parts of the country. Tillage can have an effect on water supply. One of the main reasons there's an interest in no-till and in residue management is that if we keep the residue on the soil surface, it's going to tend to do what to our water supply? Extend it, reduce it, increase it? What do you think? What does residue on the soil surface do to our water supply in the soil in terms of what plants can use? Extend it. Why? Reduces evaporation, right. So you've got a couple ways that water can leave the soil. Evaporation, which means moving through the soil surface into the atmosphere, or transpiration, where it comes through the plant and up into the atmosphere. And what do we want in terms of driving yields, increasing yields? We want the transpiration. It's going to pull some of our nutrients in. So we reduce evaporation, there's less loss of water from the soil that way, and we can extend through some dry periods. Will no-till get us through a drought that lasts 2 months as opposed to conventional? Probably not. What it may do is extend out a few extra days in waiting for additional rainfall to come. But ultimately, the same amount of water is probably going to be tapped out of the soil under no-till as it would under other types of tillage. Other things that are going to affect the way tillage and crop systems interact, our planting date, population, variety, and a little bit on our residue levels. All these things are going to have an effect on the interaction. All of these things are going to affect the fate of water in the soil. Hybrids are going to react somewhat differently in some cases. Planting date's going to have a big bearing on that. Tillage and soil characteristics. What happens when we till the soil? Well, I think I already told you when we broke out the prairie, there was a little reduction in organic matter level. The reason for this is we stir the soil up and we tend to add oxygen. And really, organic matter oxidation is like a very slow fire. It requires some oxygen. And if you take a fire and put some bellows on it or a blower on it or fan on it, you're going to increase the burning rate. And that's really what happens in a much milder sense in soil with tillage. That you oxidize this area and get a little bit of organic matter breakdown going on. We can do two things to compaction with tillage. We can cause it or we can help it, and depending on the type of tool we use and the soil water conditions. We also can have a big effect on structure with our tillage. Some of our structure develops as a result of compactive tillage. This is way back when we were looking at different types of soil structure, and I mentioned platy structure. That's one of the structural types that can develop right underneath a tillage pan. So if we're out there disking and compressing the soil at this one point, we can tend to develop platy structure that sits. And what's that going to do to water flow if we have platy structure like this? Let's slow it down. What's it going to do to roots? Slow it down or make it go horizontally instead of vertically. Tillage obviously going to affect our residue and infiltration and a little bit our soil animals. I'll talk about the sad story of the earthworms in some cases. What happens, again, soil changes with tillage, reduce organic matter, we incorporate the gross residue, so we're going to affect not only the overall oxidation of organic matter, but the depth distribution. If we're tilling and turning in that residue with, say, a moldboard plow, we're going to have a more uniform depth profile of organic matter in that soil than we would if we just go with no-till, where the stuff is just falling on the surface and decomposing there. And it's going to change our water conducting properties as it affects earthworms and residue. I've tried to use the most unusual types of tractors, unknown, very low sales volume from other parts of the world and country to avoid selecting one or more of these tractor types or tillage types to be viewed here and cause some kind of favoritism outcry. Okay? So you get to see some tractors maybe you've never seen before. How many here have a Deutz? Thought I'd be pretty safe bringing one of those in. Okay, here we go. Here's your old moldboard plow. Most of you know this stuff too pretty well, but we'll just run through this very quickly and look at the effect that it has on residue. Now, would you say, even without your line TRANSECT method knotted rope, can you notice any difference in the residue levels across this field? If you were to cast your rope with 100 knots on the right half of the field, how many intersections do you think you'd get? One or two? Most of you will figure out that this moldboard plow tends to reduce the amount of surface residue. This is a graphic illustration of this, where you've gone from about 100% down to 1 or 2. That residue's been buried, is what's happened there. That's gone. So you can probably be able to figure that out on the exam. This is what the soil surface might look like after an operation similar to this type of ridging and furrowing we get. Here's another type of deep tillage, which I don't have a residue shot to go with this, but this is a subsoiler, not used much in the Midwest. Very effective method for disrupting tillage pans in the southeastern United States. And I'll show you some stuff on that a little bit later on. And behind that, we've got some bedders and cultivators that come in and form a bed, fluff up a nice area for the roots, and then allow them to get down through a tillage pan. Here's an old standard chisel plow. What's this going to do in terms of residue? Well, we're going to have a little better story here. Leave a nice rough surface with some residue still up there. I don't know if you'll be asked to call upon your knowledge base and talk about residue reduction per trip with different tillage implements, but basically moldboard's going to get rid of it all, chisel's going to get rid of some, and disking perhaps a little bit more. Okay, that's what our chiseled ground is going to look like. And here is someone who's gotten rid of this frightful soybean residue that undoubtedly would have clogged up planters the next year. I'm being facetious here. This is a chiseling of soybean ground, and again, there wasn't much residue to begin with, and this stuff doesn't stand up to very much tillage at all. Here's a chiseled ground with the way it's going to look left over with the corn stalk sticking up. This is a pretty good environment for getting water into the soil over the winter. Chiseled ground left like this and then touched up in the spring is going to give us a good surface to work with. And disking, a chopping operation. I'll tell you in advance of my compaction section that disking is the most disruptive, compactive tillage implement there is. And it's for a couple reasons. One, when you look at the shape of a disc, when you think about it as a big plate and curved or fluted, whatever, okay, you look at that big surface area, that's well and good, but how much of that surface area is holding up the weight of the disc when it goes through the soil? There's a very small contact point, and where that contact point hits, that's bearing the weight of that implement, and it's at a fairly continuous depth, and there's a whole bunch of them. So many times we find a formation of a tillage pan, particularly in sandier soils, and as a result of disking, particularly repeated diskings. This is one of the great recreational tools in terms of a little boredom and just to get out and kind of zip around a little bit. It's a good deal. It's probably a little safer to use a field cultivator in terms of what it does to residue. Here we go. Here's just another disking with an ancient tractor shot here, and this is what you tend to be left with under those kind of circumstances. Little field cultivator and a little drag is kind of a finishing tool. In many cases, it's not terribly disruptive on the residue levels, depending how deep the things run and what kind of speed you're running at. So basically, we look at the different tillage and what happens with organic matter. No-till is going to increase the surface organic matter, no doubt about that, because you got all that material laying right up near the surface, and it's going to provide an environment directly under that residue that's a little bit cooler. It may be a little bit moister, and we're probably going to get a little less oxidation than what would occur if that material was stirred into the soil and worked in. Let's think back to our carbon-nitrogen ratio for just a second. If we take corn stalks and work them all into the soil, where they're all cut up and in contact with soil, what's the rate of breakdown going to be compared to piling up corn residue on the soil surface? It's going to be faster, right, if it's put in the soil. And what you've got is some localized areas there where you've got some nitrate supply. The corn residue sitting on the surface is going to break down much more slowly because it's not in contact with a lot of soil organisms. It could be dried out. It may not have the nitrate there to accomplish that. So when we leave material on the surface, it's going to break down quite a bit more slowly. About tillage and bulk density. Hey, we get a lot of calls during a drought year with folks saying that they've got compaction. Okay? Now why do I at least speculate this is the case? People equate compaction with soil hardness, when in actuality it's the density of the soil, the bulk density, or how much or how little pore space is in that soil, that is a truer measure of soil compaction. How many of you ever heard of a probe penetrometer? These little deals that they're a cone with a rod on it, and you can stand on the soil, push it down in, and either get a reading or feel the resistance against that cone. And that's kind of a proxy for measuring soil compaction. Now, I guarantee if you go out in July and it hasn't rained in a couple weeks, and you take your probe penetrometer out, if you don't snap the thing in half and spear yourself by trying to put so much weight to drive it in, you may be convinced that you got all kinds of compaction problems. In actuality, those measurements should be taken just a couple days after a rain so you feel the true density of the soil rather than the hardness, because soil is going to get harder and have more strength as it dries out. The bulk density would be a measurement of the actual weight per volume of soil and the actual tightness or lack of pore space that's involved. When we go out and till a soil in the spring or fall plow it, what have you, and fluff it up in the spring, we're always going to have a lower bulk density, a more aired out soil to start with than we are with a no-till. But what happens over time? Hopefully we get some rain, and that soil is going to settle down, and it's going to become denser. And so what we have is, when we look at conventional tillage, chisel plow, or other types of tillage, we have a loosening followed by a reconsolidation over the crop season. What's happening in our no-till? Our no-till is going to be initially dense, but it's going to stay about the same density all throughout the year. There is time required for no-till coming out of other types of tillage systems for it to develop the aggregation and the structure that's going to give it a little nicer tilth and be a little bit better for crop production. A lot of people are frustrated going into no-till initially because of the hardness of the soil. So we fluff this stuff up, it's all densified, and then it gradually sinks down. This is kind of a conceptual thing, looking at no-till versus conventional till over time. And some work that's been done in Minnesota would suggest that anywhere from 3 to 7 years in no-till are needed before the soil properties improve to where they're better than just a conservation or chisel plow tillage system. And what happens again, you got to allow for the biotics to take over, the earthworms and so forth, to loosen that up, and the organic matter to break down and be incorporated into those upper layers. The conventional tillage, we're going up and down every year. We fluff it up, it gets beat back down, we fluff it up, beat it back down, and so forth. And the changes on no-till occur over a longer period of time. What about our earthworms? You may get some questions about this in terms of soil organisms. Well, we do get development of earthworms oftentimes in a no-till system that would exceed those of a conventional or chisel plow system. Earthworms are vulnerable, and we're primarily talking about night crawlers here. When do they come out? Well, they come out just slightly above 50 degrees. You get a nice rain in the spring. They come out, make new friends, oftentimes start a short-term romance, develop more earthworms. And the same thing in your farming operation. This is when all these different worms are going to be out. They come out of their burrows after saturation, too. You get a heavy rain, they're going to come out and just evacuate their homes and get off on the soil surface and wait for things to dry down a little bit. During the winter and summer, they're pretty much safe. So what happens with tillage? We can destroy these vertical burrows. Most of our night crawlers go right up and down. They have a 3-foot burrow, and they might have a little side pocket, kind of like a little beaver hut that they go into in the winter and summer. But their idea, they come up and they build a little structure of organic matter over the top of that vertical burrow, and they come out and they keep their tail end in the burrow and just feed around organic matter, pull it in and feed on that and line the burrow with it. So that's what happens. And these give us some nice water conducting properties in those soils if we have a bunch of those vertical burrows. Obviously, if you come in with tillage, these burrows can fairly easily be destroyed. And obviously, tillage, too, is going to expose these earthworms. They're very sensitive to UV light, and also, the birds can eat them up. Whether this affects your overall management scheme or not is another question, but this is what happens, the ins and outs of the worms. And they do get down there. They do develop some burrows. These burrows are important in conducting water only when we get saturation. If we have a gentle rainfall, interestingly, the large holes in soil are not used to conduct water. When we get a light rainfall, it's the sponge-like or smaller pores in soils that conduct water under suction. What we need is a big gully washer, and then the large holes act like a check valve, take all this water in and conduct it down to lower levels. What we've done here is to take some dye and pond it above an agricultural soil. And we were finding this dye down 8, 9 feet in old root channels and earthworm burrows down to 3 or 4 feet. So, but the water, again, only travels under a saturated condition to get to those kind of depths. And it doesn't really use the main soil matrix at all. This stuff just travels along in the big holes, kind of like a superhighway. What are signs of compaction? This is a question you'll probably see. What are some things to look for? How do we tell about compaction in our agricultural soils? Well, the first thing is going to be reduced root growth. And there's some things you can confuse with this. What are some other things that might lead to reduced root growth in our soils? Beetles, root feeders, yeah, herbicides. Many of these things are going to typically be brought into question when we have reduced root growth, but compaction will do it. More typically, what it'll do is send out some lateral root growth. This is, again, it's going to be more in sandy soils, but if there's compaction, oftentimes you'll see roots growing down and actually going along a tillage pan. We may see some of this in southern Illinois on clay pans as well. Nitrogen and phosphorus deficiencies are possible because we need root volume or root contact in the case of phosphorus. So some early season P deficiencies would be quite likely under compacted conditions. And ultimately, some people that are truly gifted in the soils area, I've seen this guy dust off a tillage pan just by feeling the density with a knife and able to, like an archaeologist, to extract and expose high soil strength layers. But again, looking at our cone penetrometers, we can feel these layers as well. But again, I urge you to look at the idea that these need to be done at the proper water content to feel any kind of real inherent compaction rather than just soil strength due to dryness. So these are all ways we can find compaction. How do we alleviate it? Well, prevention is the best cure for sure when it comes to compaction. Staying off wet soils is the number one thing. And it's interesting, of course you'd never be out there anyway, but it's harder to compact a paddied soil, one that's totally saturated. What is the physical mechanism of compaction? What's actually happening to that soil when we compact it? Remember, a soil body is composed of solids, air, and water. What's happening when we compact the soil? Push the air out, right? If there is no air, you can't push it out. And that's what it is. It's pushing the air out that collapses the pore space, not water. You're pushing air out. But soils that are mostly wet, why are those more compacted? Now, one that's bone dry has 100% pore space filled with air, or most of it filled with air. Why can't we compact those soils? Won't move as easily, right? They've got good soil strength, and there's a lot of particle-to-particle contact. When we get a soil that's pretty wet but not full, all the soil particles are lubricated such that when compactive force goes over the top, they can slide together, pushing the air out. So that's why we get compaction on wet soils. We can alleviate it with deep tillage in some cases. I don't want to rain on anybody's parade here, but the deep tillage in the Midwest on silty soils oftentimes is not economically viable. Really, the soils that respond the best are sandy soils or loamy sands that can be quickly gone through with a deep tillage implement and loosen up and get roots to go down through. Freeze and thaw cycles help us a lot here too. If we get, we get in this kind of an area and we get a little bit of surface compaction, oftentimes just the freezing and thawing action or wetting and drying will tend to break down surface compaction. Tillage and compaction, the biggest problem we have is repeated disking. Again, I talked a little bit about the pressure point right at the bottom of that disc. Goes through, and particularly if it's repetitive. Compaction at the point of disc, and it's typically, this is a concept that people find unusual, I think. Most people, I think, would assume that clay soils compact better. They really don't. Clay soils typically have lower bulk densities, or less dense than our sandy soils. And the Atlantic coastal plain is one of the areas where this is the greatest problem. There's the big compactive tool there. Okay, I told you earlier on the geography, we had talked a little bit about the fact that there was something below Illinois, and these little areas in white indicate the areas that are most likely to undergo compaction in their soils agriculturally. They're loamy sands, they have just a little bit of silt and clay in them, and they cement up very tightly. Anybody that farmed on these soils would be more than glad to come back and farm in a clay pan in Illinois. They would think they had returned to the promised land. This is what these soils look like. You know, we've got upwards of 0.5 to 1% organic matter in a good day. Deep tillage, the subsoil bed operation I showed you before, loosens up our root zone. And I hope you can see this well in the lighting. What we have on the left-hand side of the slide here is corn, identical, hybrid, same planting date, everything else the same, planted with a subsoil and bed tillage system as opposed to just disking alone. And interesting, the farmer that I worked with, I was at North Carolina State University for a while, and the farmer that I worked with there had never had over 80 bushel of corn in this field, and just a simple subsoil bed we were able to get 120, which wouldn't be a miracle here, but he was quite impressed with that. And it's simply breaking that tillage pan and allowing rooting to go on. If you look at depth and root distribution on subsoiled versus non-subsoiled, it just allowed the roots to get down a little deeper. And there's such low fertility in these soils naturally, it's very important, particularly with respect to nitrogen and sulfur, to get that rooting depth down and also get a little additional water. Getting down towards the bitter end here, I'm going to show you just a little bit about the saline-sodic soils, and then I'll try to entertain any general questions that you might have. Really, I don't even know if you'll face these questions on your exam. I know there's quite a bit of variation. I've done a little CCA training in different states, and as you move west and north, the saline-sodic stuff becomes much more important. But you might be asked a little bit about this on the national exam. Maybe 1% of your total score will be dependent upon this. Basically, we're talking about salty soils or soils that contain sodium. Saline refers to salty. Sodic refers to the presence of sodium in these soils. So, a saline soil. These oftentimes are white on the surface. They contain a high amount of salts, but of those salts, less than 15% are sodium. What are some of the salts that we might get? What's a salt? Okay, yeah, potassium. You need a cation, an anion. It might be sulfates or chlorides in particular that are going to form. And the cations would be, say, calcium, potassium, sodium, okay? So we get a saline soil. It might have a lot of calcium chloride, maybe calcium carbonate, and this stuff is going to be present on the surface. What kind of environment in terms of rainfall and so forth would you expect to find a saline soil in? Low rainfall. Okay, why is that? You have some salts and have these different cations and anions in the soil, and you have way more evaporative demand than you do rainfall, so what's the net movement of water in that soil? It's always up. So the water evaporates up to the surface, and it carries with it these soluble salts, which are not able to evaporate with it, so they're deposited on the soil surface. Okay? So we have very salty soils. And to manage these, some crops are tolerant to this, but to manage this, what you'd want to do is to irrigate that and try to flush these salts down through and have drainage. You run into a disaster if you try to irrigate soils that are sodium dominated, or the water that you irrigate with contains a lot of sodium. What does sodium do to a soil? Anybody been around these oil fields where they pump sodium out and you get slick soil that is in a dispersed condition? Sodium attracts a lot of water with it, and you get very slick spots in the soil. The soil is totally dispersed, meaning not together, not flocculated or together in granules. Calcium tends to flocculate soils, sodium tends to disperse it. So sodium is a very bad thing for soils. The saline-sodic soils are those that are both salty and contain high levels of sodium. When I say greater than 15%, I mean greater than 15% on the exchange sites, the cation exchange sites. I think Bob Hafe will talk about that in his section on fertility, what cation exchange capacity is all about. but more than 15% of the cations are sodium. Then finally, the sodic soils alone, they have low salts, but of those salts, quite a bit of it is sodium, and these have a lot of problem again with dispersal. Okay? We get slick spots, we get problems dispersing, we get poor drainage happening with our sodium-affected soils. What kind of pHs do we get with these things? Again, it depends. If they're saline and not sodic, we oftentimes have a dominant calcium or magnesium chemistry. If we had free calcium carbonate in the soil, the pH associated with that is going to be about 8.2 to 8.5. So typically, a saline soil alone will have a high pH, but it'll be usually less than 8.5. We get into our sodic soils, they're sodium dominated. What's Drano? The stuff that, what is it, once in every day, Drano in every drain? Don't recommend that, but know the jingle. What's Drano composed of? Any idea? It's a sodium hydroxide. It's like a lye. It's got a very high pH. Well, any of our sodium-affected soils have got extremely high pHs, and this alone can cause a problem, as well as the physical problems that occur on these things. So it depends whether we've got a sodium or calcium-dominated system. How would you reclaim a sodic soil? You would need to leach it with irrigation water, and you would need to have an additional source of calcium to put in on that soil, probably gypsum, and flush that down through. You want to replace the sodium on the exchange sites with calcium, and then get back into a better situation that way.